Welcome back. I'm Paulo Shakarian, and this is the Neuro Symbolic Channel. And today, we will continue our discussion on different types of neurosymbolic AI systems using the Kautz framework. So we call this lecture Neurosymbolic Coroutines. So recently, we've been also talking about the symbol grounding problem. And this was a problem introduced in 1990 by Arnett. And it's about how can a semantic interpretation of a formal system be made intrinsic rather than just parasitic to our own thinking. So a great example of this is when we threw up some first order logic on a slide, and it had references to soccer players and predicate names like play for, and right away you could read that, you could understand what it meant because you have preconceived notions of what those predicates could possibly mean. And then we showed an equivalent in with meaningless symbols, with just like random letters and numbers. And of course, you couldn't understand what it meant, even though logically it was equivalent. And so this is the big question. How can symbols be grounded by anything other than our preconceived notions? Can this be done in an artificial system? And so there's a lot of examples on how things go wrong, especially with data-driven models. Even if you're using a neurosymbolic approach, you could still have this notion of a reasoning shortcut that can really make things go wrong. And then, of course, from a philosophy perspective, there's this Z condition, which means that you can't have any semantic commitment. So, really no prior semantics ideally should be available. Now, this is a very strict condition, but as we found, putting limits on the semantic resources available does make sense. Maybe it shouldn't be zero, but it shouldn't be anything's available, because otherwise it's not really the symbol grounding problem anymore. So in this slide, we talk about this idea of a Praxical solution, and you have machine one and machine two, where machine one operates at the object level. It interacts with the environment and identifies states based on the environment that are in accordance with its level of abstraction. Machine 2 operates at the meta level, and it coarsens the state to a different level of abstraction. And because of this, now it can extract symbols based on what's called the performance rule to associate symbols with states. Now, this has been criticized later on that this is not properly grounding symbols that will end up being composable, so that's one of the complaints about it. But the reason we bring this up is this kind of bifurcated mechanism where you have something that is operating at this kind of low object level, dealing with primitives, and then another machine that is above that is extracting symbols. This paradigm is important not only from a metacognitive standpoint, but also from this notion of a neurosymbolic coroutine, where machine one is a neural network and machine two is some kind of symbolic process. And how this object and meta level is reflected in our dual process theory, we can think of the autonomous mind. Remember, this consists of a collection of autonomous processes that just kind of react to the world. The results of this autonomous process are reflected with what's called the reflexive mind, a type 2 process that then makes decisions on if additional cognitive resources should be brought to bear. Metacognition is generally cued to reason about failures. And what we're going to talk about today with coroutines is, can this cueing lead to improved semantic understanding? So looking at this from the Kautz framework, from our roadmap of where we're at, we are on Kautz 3. Neural network converts raw input into symbols for a symbolic solver. Now, some of this will kind of borderline on, say, Kautz 5 or even Kautz 2. But and as we talked about earlier, the Kautz framework isn't, an absolute perfect taxonomy, but it is a useful one. So we will talk about neural or type 1 systems being corrected by symbolic type 2 methods, and we'll focus on abduction and NASR. So what is abduction? Well, here's Charles Sanders Peirce. And if you don't know who he is, he's America's greatest logician. He's also known for significant contributions to semiotics and also the development of quantifiers that we see in first order logic. We're talking about abduction today. And we can think of, for a given observation, such as the engine doesn't start, and we have some domain knowledge. So for this observation or manifestation, what are all the possible things that could lead to it? So we assume we have some kind of model. If the battery's dead, the engine doesn't start. If the fuel line blocked, it also doesn't start, and so on. And so based on this, we want to find an explanation. So we don't know the initial set of facts, and we have to find a set of facts that's consistent with the domain knowledge and the observations together. So if we think about this in terms of case, so your facts, so this is me teaching CIS 700, a model. If someone's teaching CIS 700, they work at Syracuse, and the result, so I work at Syracuse University. With deduction, you have the case and the model as the input, and this result is the output. Generally, you're only going to have one output with deduction. It's like solving a math problem or following a policy. With induction, you're going to have the case and the result as input. And so you could think of machine learning as kind of inductive, right? You've got your X and your Y and your training data, and you want to come up with a model. So here we have a set of rules as the model. So next is abduction. So, well, that's the other combination. You got the model and the result. So you know that, and you got to figure out the case. It's like solving a mystery or diagnosing a medical case. So looking at this, so we have this model and result as input. We have the case as output. We might also have some hypotheses, so some potential things that could plug in the gap. So maybe these are some of our hypotheses in first order logic. So there's that I teach CIS 700. Another one is I teach CIS 467. Another is I own a car. So the result we often refer to as the observation, and then we have the theory or domain knowledge. And then where we finally land on at the output is the explanation. So as you can see here, there could be multiple explanations. If all you knew is I taught at Syracuse, and your only two rules about teaching at Syracuse was you teach either CIS 700 or CIS 467. CIS 467 could be a reasonable explanation. So that would be an alternative one. You could also have explanations that have comprised of more than one hypothesis. But there's some notions here. You have this notion of covering. An explanation was cover all observations. So me owning a car doesn't cover any observations. That by itself is not covering. The parsimonious, and this idea here is to have some kind of objective function, some notion of simplicity. And so covering, we talked about this already. If the owning a car by itself is not covering. Empty set is also a potential explanation. That's not covering either. So parsimony there's a bunch of different ways to define it, and it could even be heuristic or domain specific. And so here are some common parsimony requirements. So you have subset minimality, so no subset of an explanation is also an explanation. You could just look for overall minimum cardinality. And you have ideas dealing with prioritization, grouping hypotheses according to priority, or penalizing hypotheses are weighted and you're going to minimize some function over their weights. So irredundancy, me teaching just CIS 700 is irredundant, but this other explanation that has all three hypotheses is not irredundant because it contains several explanations within it. It contains three explanations within it. Even just these two is not irredundant because both of those by themselves are explanations. Minimum cardinality consisting of just one element in this example. So if you have more than one, that's not of minimum cardinality. Okay. So concepts relating to irredundant parsimony. Relevancy, a hypothesis in at least one explanation. Necessary, a hypothesis is in all solutions. So here's two examples of that. Or these are two examples of not necessary. In this example, none of the hypotheses are necessary because you can still create an explanation. So, okay, that was a primer to help you think about abductive learning. So with abductive learning, we say there's an underlying logical language and a set of domain knowledge. And we have this training data, X's and Y's. And we have a set of primitives that are in the language of B. And we want to identify, as part of the solution, this function that maps features over the space of where the X's are to primitives. Now, the key is that the primitives are not your Y's. They're not part of the ground truth. The Y's are determined based on the deduction of the primitives and some other stuff like background knowledge and this delta C, which is additional things that get abduced. So given these observations, we have this theory, background knowledge, and the hypotheses and explanations. There are two parts. You have some extra symbolic stuff, and you have this P, the perceptual function. So in classical abduction, you want to cover all the elements, but in ABL, you're dealing with a noisy data set. So you want to, so here we're looking at optimizing, let's get the little laser pointer. Optimizing with respect to finding the largest subset of the data such that the background knowledge, delta C, and the perceptual model satisfy everything in that subset. So that seems to be a sensible thing to do. And really, this is kind of going in an iterative approach. In each iteration, you're going to learn a model P, and then you're going to abduce this delta C. A lot of this has been looked at with things like binary addition from handwritten input and other mathematical operations like that. Now, since we don't have any ground truth for the primitives, P is going to perform very poorly in the early iterations. So the idea here is you have some kind of masking function over P, over the results of P, where you just discard some of those results. So you only end up looking at a subset of the data. So we change our hypothesis to look like this. You have the perceptual function minus the masked data, union with this delta P of X, which are abduced primitives. So these are, that first delta are abduced primitives from the abduction process, the symbolic process. And then delta C is just like extra rules and stuff. And so this mask is learned along with the rest of everything else. You can think of this mask as essentially removing primitives that are most likely to be wrong. And it's okay to do that because we don't need to, because the data is noisy, we accept the fact that we're not going to be able to entail 100% of everything in the training set. So we can reframe the problem like this. So now we're learning hypothesis H delta such that the delta of P of X, so the number of perceptions that get removed, are within a certain bound. We'll say that's M. Okay, so how do we train the perceptual model? Well, what we do is we can use reassigned labels from the abductive set as ground truth. So the new set of labels for the primitives are going to just be what's abduced. Now, of course, every time you abduce labels, of the primitives, or you abduce the primitives, you are not getting that information from perception. So that link between perception and symbolic process is being severed when that occurs. Now, in the early stages, you're going to want to do a good deal of that because the perceptual model will not be so good. The abduction routine gives you more data about what the primitives might be, and that's the same data that is then used for training the model in subsequent iterations. So we could see this working as follows. So we have machine learning input, a perceptual algorithm, and then in the derivative-free optimization of the delta function, that's along with the solving of the abductive program, you see that certain outputs of the perceptual model need to be revised. And that's okay, because then that goes and adjusts the ground truth that's used to train the perceptual model. So in experimental results, accuracy is quite good. They compare it with some standard machine learning, convolutional neural network. Also, they look at human performance on the task. And so this turns out to do quite well. They also have this, what they call this RBA data set, where you have these sort of made-up symbols that correspond with mathematical operations, but they, don't really have any meaning. You also can look at what happens with loss. You see on both sides with the accuracy of the perceptual model and the results of the abduction. And you see what happens is as you progress with abduction, you get more and more consistency as time goes on. The inconsistency is due to primarily the failures of the perceptual model and, having to remove elements with the mask. And as that occurs, it is able to focus on what makes it consistent, producing new training examples or new labels for the training examples that could leads to quick improvement on the perceptual side. Now, what's interesting to note is that this abduction of this delta C, this additional information, it adds a layer of complexity. Later papers that followed this work stopped doing that and focused mostly on the perceptual model. Also, if you look at the code and the logic, there's like a lot of engineering to kind of set up how some abduced rules can fit into the framework of a given problem. So this was sort of avoided in later work. The other thing too, of course, doing logic-based abduction, it's, of course, very difficult from a complexity standpoint, as by the shown complexity results in this slide. Anyway, so this work was later extended with what's called abduction, abductive learning with new concepts. And so they used an out-of-distribution detector to identify when the model is now in a situation where there might be a new class that needs to be added. So here is the idea. You have you could have new things abduced at kind of two different levels. So maybe you don't have a new concept, or maybe you don't have a concept that's about one of your labels. So we have, here we see in an example, we have this 9. And so, well, can we add a new primitive for that that wasn't in the training data? No, and what can we conclude about it? With the second case, we can also have a new target concept that can emerge out of the reasoning level. So again, we have an underlying logical language and domain knowledge, and we have the data set with the X's and Y's. And we say that one of the values for Y may not appear in the head of a rule in B. So you can't possibly conclude that. And so we also have this set of primitives, but we say that one of the primitives is unknown. So we know, so we have incomplete knowledge of the language, in other words. And then the unknown primitive doesn't appear in any of the rules either. Okay, so how do we go about doing this? We don't have any background knowledge on this entirely new thing. Well, the initial run of the perceptual model, we run a new concept detector and add that label new based on the concept detector. So we say that the concept detector is G, and we say label new is added if G says there's one. And this is, they just use kind of an off-the-shelf OOD detector from prior work. Then once they do that, they use inductive logic programming. They use something called ILAS, which is a ASP ILP solver. And so they learn new rules that use the new concept. Now, these rules may be inconsistent with the existing knowledge base. They have to do this conflict resolution procedure. And so we could see the way that this conflict resolution procedure works is it makes new, it tacks on negations to the body of the rules that are in conflict. So we might have, so you see at the top, you have divisible x1 comma 3 and divisible x2 comma 3, then it's new. And then you have divisible x1 comma 2 and divisible x2 comma 2, and then it's even. Now those could potentially be in conflict, say if something is divisible by 6. So what you do is you, by tacking this negation on, it doesn't allow that to occur. So here, even is no longer defined as anything that's divisible by 3 is no longer defined as even in this example. So now that we have all that figured out, we can do abduction, or we can do abductive learning But here we no longer have the delta C. That kind of got dropped, but we're doing it with respect to perception. And now we update the model. And once we start updating the model, now the new primitive is baked in. So the other interesting thing they do is they look to match the new concept with concepts from a knowledge base. So here you have a semantic resource and that's available. And the idea is, can they align the new concept with something in this knowledge graph? This is probably one of the weaker parts of the work. It's very specific to this case, but it was interesting nonetheless. So they did this using some common sense knowledge graphs, and the idea is rules containing new primitives are converted into triples and compared with the knowledge graph. And so they identify a subgraph of the knowledge graph, and then they create an embedding and convert the new rules into triples that contain the symbol new. So then they're going to find the entity in the knowledge graph where the embedding is maximized when substituted for new in all triples. So you would have this triple, for example, that describes how a new piece is in a chess game is being used. Now, why is this important from a symbol grounding perspective? Well, the outlier detector can help us find a new primitive, but it doesn't know what it's good for. ILP can help us know what it's good for. And ABL can ensure that these things are learned in context of the other classes and domain knowledge. And the knowledge graph comparison now actually grounds it in a defined symbol. So you're hitting on a lot of things, and notice that the authors here are pretty careful not to let anything about this new concept leak into their framework. And so they experimented this with some very simple cases. They looked at MNIST, less than with new digits, chess with new pieces and multiples of 3. And they compared it with, machine learning and standard ABL. But what's interesting here is now you could see, the perception and reasoning accuracy is quite good here. There's limits to what the others can do because they don't have the complete set of concepts. Here, ABL and C is creating the new concept just using the OOD detector. Okay, so back to our dual process chart. So perceptual level and for humans, this is more than perception. We do approximate symbolic reasoning in our heads all the time here. And we can do this very quickly, and we can kind of guess how things turn out, even if we don't take time to reason about it. And many people, we all do this associatively. But we also have little cues that can tell us when we think these very quick reasoning instances might be wrong. And when that happens, we employ the meta level to correct those errors. So here is neural attention for symbolic reasoning, or NASR. And the idea is you have a neural solver. So you perceive something and you use a neural network to do some reasoning on it. Here it's reasoning about what a scene graph would look like. And then you have this mask predictor, which is trained on erroneous data that is usually generated. And that predicts which parts of the output of the neural solver should be masked. And then correction occurs by using a symbolic solver to fill in those blanks. So here is, again, the schema of it. So your perceptual model, this is a base perception. It's trained on primitives. And it's much like the convolutional neural network that was in SatNet, so not a big deal. Solver neural network, this attempts to solve the given logic problem. And the authors of this paper actually use this to solve the Sudoku problem, just like with SatNet. But the mask predictor is where this gets really unique. So this is trained on separate data to identify errors in the solver neural network. And this is done by just taking data that are, in this case, you could think of Sudoku puzzles or even scene graphs, where we have correct answers, and we purposely, through an automated process, degrade them in ways where they are inconsistent or cannot be verified. So then you have finally the logic solver, and the output of the solver is what's used to correct the output. Now the whole thing works together in a reinforcement learning loop to further refine parameters, and that turned out to be a really important step here. So, so one way of doing this was taking the ground truth of the original data set and randomly replacing components with noise. And what this does is this mask predictor, by identifying errors, it simply masks those symbols out, and you are again returned with a partial solution that goes to your symbolic solver to fill in the gaps left by the mask. So here's a Sudoku example. So we have this input and output. Here's the reward function used in reinforcement learning, and this is based on both for Sudoku, correctness of the board as well as correctness of individual cells. And it's interesting they did that because at the perceptual level, you want to give RL some kind of signal in the early stages that it's going in the right direction. And so looking at the individual cells on the board allows it to do that. But then as it progresses, it's going to start more correcting, large, it's going to start valuing more of how that everything is consistent, where the board is the board gives the correct answer. So here are the results. So this turns out to be both more scalable and more accurate when compared with things like SatNet, and as well as neural ASP, which has some intractable computations involved in the probabilistic component of that. So what's interesting here is this doesn't rely on changing the perceptual model, but rather identifying where it makes mistakes. The logic itself doesn't need to be differentiable. In next lesson, we'll talk about logics that are differentiable. We talked about that, though, with the Kautz 4 systems like differentiable ILP and logical neural networks. The other nice thing about this framework is Sudoku is more of a challenging benchmark than this MNIST stuff. All right, well, that's it for today's video. Thank you for tuning in, and don't forget to like and subscribe.